Well, welcome to the first of our Cambridge Physics Centre lectures. It's good to be back after a long time during COVID where we've had online lectures and you sat in. Hello? Okay, so you sat down at home doing that and listening to virtual talks. It is good to get back to a real talk. I'm going to introduce our speaker. Our speaker is actually Nuala O'Flynn. If you were expecting Dr. Emma Curtis-Lake, she will be joining us later. So unfortunately, Emma got called away. She's involved with the ultra-deep field part of the James Webb Space Telescope and got caught. They've just released the data, and so she's away at the moment in Arizona, just deciding what to do with that data and where it's going. So Nuala, thank you very much. She stood in at the last moment, but Emma will be joining us at the end of the meeting online from Arizona. So we've got a Teams meeting set up, live link coming from Arizona. Just to introduce our speaker, so Nuala O'Flynn, she's the SEP Net and Ogden Outreach Officer for the Department of Physics, Astronomy and Maths at the University of Hertfordshire. Nuala joined the SEPNet team at the end of 2019 after graduating from the University of Sheffield with a BSc in Physics and Astrophysics. And she works to connect the public with current research of the department and to show people that, well, anyone can study physics if they want to. Just before we do that, I should say a brief point about fire exits. We're not expecting any fire drills, but so if the fire alarm does go off, you can see the exits either side here or at the back of the lecture theatre as well. So do make your way quietly to those exits. So without further ado, I shall introduce Nuala. Thank you.
I'm just going to turn off the side images and then we can get started. Okay, hi everyone. So my name is Nuala. Can the people at the back hear me okay? Can everyone hear me okay? Yeah? Okay, good. I'm standing in for Emma today, so we work together, but she had to get called over to Arizona. So this is her talk and her slides, but I'm going to do my best to represent her talk for her today. I'm a Physics Outreach and Public Engagement Officer, so I work on the communication side of astronomy, which is a job you might not have heard of before. So I feel very lucky in my job. I didn't want to go down the PhD route, but I love astronomy so much. And in my job, I still get to learn about all the groundbreaking discoveries that there are in astronomy, such as the Webb Space Telescope, which is the most exciting thing in astronomy at the moment. So has anyone heard of the Webb Space Telescope before? Yes, some of you. Okay, it's got some nods, got some hands. So quite a lot of you, I'm assuming. But we're going to start at the beginning of this with the launch of the telescope. And this was the best present for astronomers on Christmas Day of last year. If this is going to work. It's not. Thinking the sound isn't working, but which might be an issue later on because I think we should be hearing some rocket noises right now. But yeah, so we're just viewing it as it gets launched into space. And this is not a real image, but a photo image of it. And this was a real video of it. So they didn't think that they were actually going to be able to see footage of the Webb Space Telescope going off into space, but they did manage to record some footage by putting a camera on the rocket as it was released into space. So that's it, going away and part of it unfolding as it goes out into space, which is really, really cool. So this is the size of the telescope. So this is the largest telescope that's ever been launched into space. So we can see up here, we've got the Hubble telescope here, which you also might have heard of, and we've got a little person here next to the mirror, the primary mirror of the Hubble Webb Space Telescope. And then we have the JWST here, and you can see how much bigger the primary mirror is compared to the Hubble telescope. And here you can see the person. So this is actually 6 meters across, so it's absolutely massive. And the whole of the telescope is about the size of a tennis court. So it's really, really big, and it was too big to actually put in full, into a rocket, so they had to fold it up. So they kind of did some origami where they folded it up all like this and they put it into the end of the rocket, and there was a lot of incredible engineering that went into that. And then as it came out of the rocket, it was able to unfold and go to its point where it is in space. So we can see here where the telescope is going around at a point called L2. So L2 stands for the Lagrangian point 2. So this is a special point. There are 5 of them that are in space in between the Earth and the Sun, where the gravity of both of those objects isn't pulling it one way or the other. So the telescope can stay in a fixed place at all time, which is great because it doesn't have to use a lot of energy constantly having to move where the telescope is in space. And it also means it can stay in a fixed way, which you can see up here, where it's facing away sort of on its side rather than flat, it's on its side. And we want to do this because the telescope needs to be really, really cold. So the telescope is cooled to about minus 223 degrees, so really, really, really cold. And one of the instruments on it called the MIRI is cooled to minus 266 degrees. So it's gone out to the L2 point, which is about 1 million miles away, so it's pretty far away. And its orbiting allows the mirror and the instruments to always be protected from the heat and the light that's coming from the sun and from the Earth as well. So we want to do this, we want it to be really, really, really cold because it uses something called infrared light. So a lot of you, I'm assuming from school, will be familiar with the electromagnetic spectrum. So the Webb Space Telescope is looking in the infrared light here. So telescopes like Hubble mainly have been looking in the visible light, and we've got Spritzer here, which looks in infrared. And we have a bunch of other telescopes as well that look across the whole of the electromagnetic spectrum, but this one is looking specifically at the infrared, and I'll talk more about why we're looking at that in a bit. So this is a video of what infrared light looks like. So we all see at the moment using optical light. So we actually do experience infrared light as heat, so any object that gives off like thermal energy or heat, we're able to feel that. But if we were to see through through infrared light, this is what we would see. So we can see this woman here, and we see where she's giving off heat in her face and where is cooler as well. So infrared light provides us different information, and it's really, really important in observational astronomy. Ooh, sorry, I didn't mean to play that again. There we go. But why did we want to launch it into space? Does anyone know? So this was a very, very expensive telescope. It was like $10 billion. So why didn't we just keep it on the Earth? Yeah.
The telescope might, well, the infrared in the air and from Earth might interfere with the telescope too much.
Yeah, exactly right. Yeah, so on Earth we have an atmosphere. So our atmosphere is pretty good for life on Earth because it protects us from a lot of really dangerous electromagnetic waves that are in space. So very high energy ones like gamma rays, and also a lot of infrared light as well. So our atmosphere protects us. We wouldn't have life on Earth if there wasn't our protective atmosphere, but it's not great for astronomers because it means we have to spend loads and loads of money getting telescopes into space so that we can see in the infrared. But why would we want to see in the infrared? Does anyone know why the infrared's really good for astronomy? Anyone? Yeah?
Maybe look at the stars and some other things that only require that infrared, which we can't see with visible light.
Yeah, exactly right, yeah. So there's sort of 3 reasons why we've put infrared light. I don't know why I keep saying we, I didn't do anything. I have nothing to do with JWST, but why infrared? So the number 1 reason is we can peer through dust and even see dust as well. So these were some photos that were taken by Hubble. So we can see here, this is a very famous picture called the Pillars of Creation. So we're looking at it here in the optical light. So you can see these 3 pillars here. But when you look at it through infrared light, which is this image here, you can get so much more information for it, and you can see behind that dust, and you can see all of the star formation that is going on inside these pillars of creation here. So you can kind of think of it, if you put your arm, if you were looking at it like this, we can all see my arm right now, but if I put it inside it like a bag or something like that, if I got an infrared camera and looked, you'd still be able to see my arm because it's giving off heat, and it's the same as these stars. So we can see them because they're giving off heat, and we can see through the dust. So here's what our own galaxy, the Milky Way, looks like. So at the bottom, we have here, we've got the optical. So if you went to like the southern hemisphere, like Australia or somewhere like that, you would actually be able to see the Milky Way looking like this from Earth. You can see here these sort of very dark patches are all of the dust that is in the Milky Way. But if we start to look in the near infrared and the mid infrared, you can see all of that stuff that's going on behind it. And that's the kind of stuff that we want to be looking at when we're in space. So dust blocks a lot of our observations. So that's why we want to use the infrared light. So this was the first image that the JWST released in July of this year. So this is my favorite image because I think it's really, really beautiful. And it was called the Cosmic Cliffs. So what we're looking at here is actually a lot of star formation. So if we go to the next slide. So we can see here what we were actually looking like is a part of the Carina Nebula, which you can see here. So the young stars here were super energetic, and they have really energetic winds, and they have actually cleared out that sort of bubbly space that we can see here. And then we're looking at the edge of it in that image, and it's creating an incredible star forming region below. So we have a look at what Hubble took of the picture here. So this is what Hubble sees in the optical, and then we can go back and forth between them, and you can see how much more of those stars that you can see. So look at all these stars here. If we go to optical, you can't really see any of that anymore. But if we're looking in infrared, you can see, get and gather all of this information for it. So this is the death of a star. So we've gone from stellar birth to stellar death. So there are actually two stars here. It's called something called a binary star system. So we can see the stars here, but on this side of them, you can actually see two of them. And the little fainter one here has died, and it's produced all of this gas and dust, and it's shooting it out, and that's why we're seeing these rings surrounding it. But yeah, so these two images, we can get a lot more information out of it just by looking in infrared light. So here we have a picture of the James Webb Space Telescope's one, and then we're looking at it at Hubble's again. It's going to be a recurring theme throughout this talk. We're comparing between the JWST and the Hubble to see how much better this telescope is at gathering information about these objects in space. So that's it, JWST and the Hubble as well. So the other reason why we like to use infrared light when we're looking at space is it's great for investigating planets. So this was an image that Hubble took. It looks kind of weird. It kind of looks like an eye. So this part here is actually something called a chronograph, which we put in front of the star, the host star, so that it blocks out all of the light, because what we're looking for is we're searching for a planet outside of our solar system. And you can see here in this little tiny bit that it's seen a planet over the years slowly moving around this orbit. And this ring around it is just a ring of dust as well. So we want to try and find exoplanets. So exoplanets are really, really difficult to find because they don't give off their own light. But what they do is they give off heat. So that's why infrared light is really, really good for finding planets outside of the solar system. So this is the first image by the JWST it took of an exoplanet. So this exoplanet has the lovely name of HIP 65426b, which really rolls off the tongue. And you can see its images of the planet here, which are a lot clearer and better And this is amazing because it's a planet outside of our solar system. And this star here is actually where the host star of this planet is, but it's been blocked out by a chronograph as well. So one of the other most exciting things that the Webb Space Telescope is going to be able to do is atmospheric compositions of planets outside of our solar system. So what we're looking at here is the atmosphere of a hot gas giant, the exoplanet WST 96b, and we've actually found water vapor in its atmosphere, which sounds pretty exciting, but this planet is about 22 times closer to its host star than we are, and it also orbits it every 3.5 days. So it probably doesn't have any life, or any life that we know of, but this is one of the first planets we found with water vapor in its atmosphere, which is really, really exciting. So what this is here is something called spectroscopy. So I'm going to play a video now, and I'm really hoping the sound's going to work. We'll see. If not, I'll have to do something, which is going to explain how we get a spectroscopy of a planet and how we learn about its atmosphere just by using light. So much for your patience. So this is a video that's going to show you how we find out the composition of atmospheres of planets outside of our solar systems.
How do we learn about a planet's atmosphere? How do we know what's in the atmosphere of an exoplanet? The majority of known exoplanets have been discovered because they partially block the light of their host star. This is called a transit. During a transit, some of the star's light travels through the planet's atmosphere and gets absorbed. The light that survives carries information about the planet across light years of space where it reaches our telescopes. However, the planet is very small relative to the star, so it is still very difficult to detect, which is why we need a big telescope to be sure to capture this tiny bit of light. So how do we use a telescope to read transit light? Stars emit light at many wavelengths. Like a prism makes a rainbow, we can separate light into its separate wavelengths. This is called a spectrum. Visible light appears to our eyes as the colors of the rainbow, but beyond visible light there are many wavelengths we cannot see. Now back to the transiting planet. As light is traveling through the planet's atmosphere, some wavelengths get absorbed. Which wavelengths get absorbed depends on which molecules are in the planet's atmosphere. For example, carbon monoxide molecules will capture different wavelengths than water vapor molecules. So when we look at that planet in front of the star, some of the wavelengths of the starlight will be missing, depending on which molecules are in the atmosphere of the planet. Learning about the atmospheres of other worlds is how we identify those that could potentially support life, bringing us another step closer to answering one of humanity's oldest questions: are we alone?
Okay, so I hope that video explained it pretty well. So even though this isn't quite as exciting as maybe the cosmic cliffs, I think it is really, really incredible because we're looking at an atmosphere's planet outside of our solar system, and it is in the hunt for life and maybe life outside of our solar system, which is super, super exciting. So, moving on, the last reason why we wanted to use infrared light is to explore the history of the universe. So this takes a little bit of explaining, so I'm going to do this in a couple of steps. So what we're looking at the moment is the speed of light between the Earth and the Moon. So it takes about 1.255 seconds for light to travel between the Earth and the Moon. And you might have heard of before that it takes about 7 minutes for the light from the sun to reach us. So, for example, if the sun was to instantly die right now, it would be 7 minutes before we on Earth realized it, because the light takes 7 minutes to travel from the sun to the Earth. So you can think of it kind of like if you were to write a letter with a date on it or something like that, or a bit of information. If you write the date and then you sent it out across the universe, maybe like 100 million light years away, by the time they received that letter and they opened it, they'd see that the date was 100 million years out of date. So it's kind of like gathering information from really, really far away. Light takes a long time to reach us from really far away places. So we're looking back in time, essentially. We're getting information which has been sent to us a long time ago. So we're able to look back in time, which is amazing for astronomers because then we can see how things were formed as well. This doesn't explain why we want to use infrared light. So leading on from this, Edwin Hubble, who's this gentleman here on the left, about 100 years ago discovered that things that were moving further away from us were actually accelerating as they were moving away. So the further away something is, the faster it's moving away from us. So that's what he discovered. So what this means is something that you might have heard of, which is called Doppler shift, so which I think you do learn about in school. So if you've ever heard an ambulance going past you, you can hear that sort of pitch changing as it's going from one path and it goes past you. You hear that sort of sound change, and it's the sound waves that are getting shrunk together and pushed away. So we can see here we've got an observer and we've got an object, and the object is emitting light. So as the object is moving towards the observer on this side here, those wavelengths are getting squished together and together, and what happens is the light shifts into the blue end of the spectrum. So this is what we call blue shift. But if you're this other observer over here and the object is moving away from you, then the light will extend, will expand, and will shift into the red part of the spectrum, which is what we call redshift. So objects that are moving away from us, or objects that are really far away and moving away from us even quicker, which means that they're shifting into the red part of the spectrum of light. So what we can see here is the spectrum of a galaxy. So this galaxy is really far away from us, which means its whole spectrum, so this part, has been shifted. It's been redshifted because it's moving away from us, which means that the Hubble telescope isn't able to look at the spectrum of this galaxy. It can't see it because that spectrum has been shifted. Whereas the James Webb Space Telescope is able to see it because it's using infrared light. So it can see a lot of the spectrum of this galaxy, and it's still able to gain information on it. So that's why infrared is really important, because we're able to look back in time and see these galaxies that have been redshifted. So what we're looking at here is another image that was released by the James Webb Space Telescope. So this is called Stephan's Quintet. So you can see the 4 galaxies here, and there's another one down here as well, but these ones are really, really far away, and they're moving away from us as well. I think they're about 400 million years away from us, and this one's about 50 million years away from us. So you can see here, this is the picture that Hubble took of Stephan's Quintet. And if we go, I don't know why this keeps on working. If we go back and forward between these, we can see the differences in the image and how much more information we get. So if we're looking at this part here, up here, you can see that when we take it with a JWST, you can see so much more information about that dust and the interaction between these 4 galaxies here. But how far back in time can Hubble look? And how far back in time can Webb see? So here we have the history of the universe. So this whole wheel here is showing the entirety of the history of the universe. So this point here is the first human, so that was about 2.8 million years ago. Then all the way down here, we've got the formation of the Earth about 4.5 billion years ago, which is around about when the solar system formed as well, going all the way back to the formation of the Milky Way, which was about 13.6 billion years ago. And this arrow here is showing how far back Hubble can see. So it can see to about 400 million years after the Big Bang, which is like a pretty long time ago. So why are we interested in this part of time? Why do we want to see those 400 million years after the Big Bang? So we can have a look at this by looking at the whole history of the universe. So this has been stretched out a bit, the early times, so you can see everything, because it all happened very quickly in the beginning. But what we're looking at here, we're starting with the Big Bang, then we've got something called the cosmic microwave background, And then we've got neutral hydrogen and helium forming here. And then we've got the first stars and the first galaxies as well. And you can see that Hubble is here. So it can't see any of the first galaxies that were formed. It can't see any of the first stars that were formed. So we don't know about any of this at the moment. We can only see as far back as this point here. So a lot of interesting and a lot of cool stuff has happened here, but we don't know anything about it. So this is how far back the James Webb Space Telescope can see. So about 70 million years after the Big Bang, which is absolutely incredible. So this neutral, this neutral hydrogen and helium form some of the first ever stars, which we're going to be able to see here. And then from there, it forms some of the first ever galaxies. So the James Webb Space Telescope will be seeing back in time further than we've ever been able to see before, which is incredible. So what has Hubble found in the early universe, and what will Webb do better? So we first have to find those very, very early galaxies. So what we're looking at here is the Hubble Ultra Deep Field. So this took hundreds and hundreds of hours in order to take a picture of a very, very small patch of sky. So if we look up into the sky and take about 1/10 of the diameter of the moon, like in the sky, that's how much of a piece of the sky it is. So it's really tiny, but it contains about 10,000 galaxies in it. So this is actually why Emma's not here today. So the Webb Space Telescope's taken the exact same photo of the same part of the sky, and that data just got released, so she's had to go to Arizona to have a meeting about it. So hopefully we'll get to see that image very soon as well. And we'll be able to see even better how much more Webb is going to find of these really, really early galaxies. So this is the earliest, some of the earliest galaxies that we've been able to find with Hubble. And this is what we think we're going to see. So this isn't a real image, this is a computer simulation of what we think we're going to be able to see with the JWST. And hopefully Emma will have some great news about what they're finding out in Arizona at the moment. So another thing that's super weird in space is something called lensing. So I'm going to play a video about this in a second, but just to demonstrate it to you first, we've got, here we can see a lot of galaxies. There's a big group here. And can you see these like weird, long, sort of stretched out things that's happening here? This has happened all because of gravitational lensing. So I'll play a video and then I'll talk about it more. I'm hoping the sound works. Come on.
How is gravity like nature's magnifying glass? To find out what the universe was like in the beginning, we need to study the most distant galaxies, whose light has been traveling to us for billions of years. But the farther away a galaxy is, the fainter it appears. That makes distant galaxies very hard to see, even for the most powerful telescopes, because they can only collect so much light. Fortunately, nature can provide a helping hand. According to Einstein, the gravity of massive objects can be so intense that it can warp the fabric of space-time. Light, which normally travels in a straight line through space, can show us where this distortion occurs. A very massive object will warp space and bend the path of the light. In a sense, warped space acts like a magnifying glass. A magnifying glass collects and bends light, making a light bulb, for example, appear bigger and brighter. Warped space can do the same thing to light from a galaxy. So what acts like the biggest magnifying glass in space? Galaxy clusters are the most massive things in the universe with the most gravity. When light from a very distant galaxy passes through a cluster, it is amplified and distorted, with the cluster acting like an imperfect magnifying glass. Light that would have gone in other directions gets bent toward our telescope. That lets us see the very distant galaxy in more detail. This effect is called gravitational lensing. Without this natural boost from gravity, it would be impossible for our telescopes to see far away enough in space and time to study galaxies in the early universe.
The Hubble Space Telescope has made use of gravitational lensing to see many distant galaxies. And the larger James Webb Space Telescope will be able to find galaxies even fainter and farther than we've ever seen. With Webb, we will look for the very first galaxies to form and really learn about the early universe.
Okay, so hopefully that explained a bit better about what is gravitational lensing. It's quite a crazy concept, to be honest, but that's what you're sort of seeing here. So there's a galaxy cluster at the center of this image here, and the galaxies that are behind it are getting bent around it, so we're able to see even more distant and even older galaxies because of gravitational lensing, which is really cool that that happens, so we can study the early universe. Oh, this is an image just flicking between the Hubble and the Webb. So you can see how much more detail of these very, very distant galaxies you get in the Webb. Hubble, you can sort of barely make them out. They look pretty horrible, to be honest. But here you can see distinctive details. You can see the spiral arms. You can see the supermassive black hole at the center. It's really incredible. So this is a visualization of a patch of sky that Webb took a picture of. So we've got loads and loads and loads of galaxies in here, and they're exploring all of this at the moment to try and find some of the earliest galaxies in our universe. So these are just some patches that were up on that previous screen, and these are some of the galaxies that are in this image. So they're all so different and contain so much information and learning about astronomy that's going to be changing over the next coming years as we get more knowledge from the Webb Space Telescope. So this was a paper that was released that caused a lot of controversy in the astronomy community because someone said they found a galaxy of redshift 20, which is like the oldest galaxy ever found. But lots of people weren't very happy about this and don't think it's true. So this was, approximately 230 million years old. So this is their graph showing it, but this hasn't been agreed with by others, so they don't think that that was right, but they're going to be using lots of different methods to determine the oldest galaxies out there. So this is the one that Hubble found, which was at redshift around 11.5, so when the universe was approximately 400 million years old. So what Webb is going to be doing is going to be taking spectra of these galaxies. So we can take a photo of them and sort of estimate how old we think they are, but without the spectra of the galaxy, we can't exactly determine how old it is. So what Webb will do is we'll be able to determine the exact age of these galaxies, and then we'll find out if that paper that said that galaxy was Z20, if that was actually right or not, once the spectroscopy data has been analyzed, because all of these are part of the galaxy, so it takes a very, very long time, and this was only released, I think, in July, that image, so they're going to take a lot longer to figure it out. So it also is going to help us find those first stars. So by looking at those spectroscopic, I'm saying that word wrong, let's just move on. We'll be able to find out whether we're only seeing hydrogen and helium. And as I was showing you earlier, in the very, very early universe, there was only hydrogen and helium. Those other elements hadn't been created yet. So the first stars were much more massive than our sun, probably about 500 to 1,000 times larger. And eventually they exploded in a process called a supernova, and will eventually release more elements that we know, heavier elements like carbon and nitrogen. But if we look in those, what we were looking at previously, here, and if we find just hydrogen and helium in them, then we know that we will have reached the first stars in the universe. So this is looking at a galaxy composition and its breakup, and we're seeing hydrogen, oxygen, neon. So this isn't something from where it was the first stars forming, so we're looking at a little bit later here. Oh, it says there, 13.1 billion years ago. So what galaxies might Hubble have missed? So Emma's got a really fun analogy for this, of thinking if you were an alien. So if we can think of ourselves being an alien, and if we get placed down on Earth, but we land in a primary school, so we'll have an idea of sort of what human beings are like, but after a while we might be like, are they always this energetic? Are they always this small? It's not the full depiction of what all human beings are like. But we can think of Webb as kind of being like if we were to be an alien and get placed down instead in a busy metropolis where we're seeing all different people, all different ages. So this is the comparison between Hubble and Webb. The Webb Space Telescope is going to be able to look at all different types of galaxies and really get a good picture for the variety of galaxies out there, whereas Hubble has such a limited view of it. And that video is going to keep going. So this is just showing some of the early galaxies as well. This is supposed to play. Yeah. So this is again showing a comparison between Hubble and the Webb Space Telescope. So you can barely see anything with Hubble, you're missing out so many details, so many galaxies, but with Webb you have all of these galaxies in there, and we're going to be able to discover some of the earliest galaxies in the universe because of this. So yeah, thank you so much for listening. That's the end.
Thank you very much for this really fascinating talk, and fascinating to get an overview of all of what has happened with the James Webb Space Telescope. It's exciting times we're in, seeing that launched and getting those first pictures back. We've got a bit of time for questions, so either if you've got questions for Nuala, or I think we've got a live link up with Emma as well over in Colorado.
Yeah,
so, we've got to need to use the roving mic so Emma can actually hear us as well.
She should be joining soon.
So, do we have any questions?
The other roving mic. Yes.
Okay, so do we have any questions either for Nuala or for Emma? See any hands up? Do you want to see any hands up for actual questions? Right, here we go, yes.
How do we get the photos back from the telescope?
Is Emma here?
Okay, so the question there was, I don't know if anyone heard that, how do we get the photos back from the telescope? So, Emma, I don't know if you... is Emma there?
Emma's not here. Sorry, what was
Okay, so Nuala, how do we get the photos back from the telescope? That's the question.
How do we get the photos back from the telescope? Oh, so it just sends to the Earth using electromagnetic radiation. So that's how we do it. So the same way that we send information on Earth to each other, we use radio waves, so we're sending information back using electromagnetic radiation.
Great, thank you. Any more questions? Any other questions? Great. Emma, hello. Good you could make it. Great, that's good. So welcome. It's good to see you. I'm glad you're able to join us from Colorado. We've got a big audience here, so we've got some good questions coming up. Member of audience here, so we've got a question at the front here.
I just wonder what the sort of key technical innovations were that enabled Webb to happen now that are kind of different from Hubble. You know, obviously technology's marched on, but were there any kind of key innovations or key changes in technology that enabled it to happen?
I know for the mirror, it was so that... Oh, you're not seeing that and I'm seeing it. So the hexagonal shape of the mirror, that was a new way of technology that they moved. So each of the individual... I've got a little thing here, you can see the mirror. So each individual hexagon here can move individually, and that was a new technology that was developed for the Webb Space Telescope, and it means that it can take better pictures of the universe as well. Emma, I don't know if there's anything else. That's all I know. So I'm sure there were lots of other stuff as well.
Yeah, actually, the infrared detectors at the time of Hubble, that sort of thing, that technology was not available. So being able to do these sort of high-resolution images in the infrared, that required completely new technology. So we couldn't look at the universe in this detail from infrared wavelengths.
I know I really want to.
Okay, so got some other questions in the audience. I can see here. Okay. Pass the mic on.
So you have said that, obviously, we learned it in GCSEs that there's redshift and everything, and it accelerates. What happens if something accelerates close enough to the speed of light that we won't be able to ever see it, and it's going to go past us? Would this be possible?
Emma, do you want to go?
I didn't hear this question very well. Is it a microphone that you have to hold very straight to your...
I can do it like that.
Could someone repeat the question?
Miss, can you repeat the question for Emma?
I can repeat it. So, if I can remember it. So he was asking what happens if something does, what were you saying? If something does go to the closest speed of light?
Yeah, accelerates with redshift so far away, and it accelerates so fast that we won't be able to ever see it ever again.
Okay, so yeah, if something is so far away from us and it's accelerating so fast that so close to the speed of light that we won't be able to see it.
What is the question? Like, would we be able to see it if it's moving so fast?
Could it be going so fast that we wouldn't be able to see it?
Is it possible?
Yeah.
That's an awesome question, yes. We often hear this thing of the observable universe, and that's the region of the universe where the light has actually been able to travel to us. There are regions of the universe that have moved away from us so quickly that the light hasn't been able to travel to us within the age of the universe. However, some of the things that we can see when they emitted their light, sorry for the background noise, when they emitted their light, they weren't traveling so fast from us, but now they are traveling faster than the speed of light away from us, because things have changed so much in the 13 billion years since, those photons started on their travel to us. So I hope that makes sense. I hope that answered the question.
Okay, does that answer the question? Okay, so do we have any other questions? You can see at the back there. I'll just pass the mic back.
What's the limits to how far back in time we can see with a powerful enough telescope?
Could you repeat that, sorry?
What's the limits to how far back in time we can see if we have a powerful enough telescope?
So Emma, the question was, how far back in time can you see with a powerful enough telescope?
With a powerful enough telescope. So Planck has seen back to the cosmic microwave background, which is the furthest back we can see with light, because before that light would get scattered. And for us to be able to see something, we need light to travel to us in a straight line. But that's not looking at galaxies or stars. The answer in terms of galaxies and stars is if we had a powerful enough telescope with JWST, we should be able to look back and see the very first stars that have formed. So within 70 million years of the Big Bang, with NIRCam, which is one of the instruments on board, we can see that. But we may have to sit for too many hours to see them. They may be too faint for us, we don't know yet, but we're searching for them.
Right, thank you very much. Any other questions? You see a hand up at the back over there.
So what rocket was used to take the James Webb Space Telescope, and why did they use that?
So I don't know if you heard that, Emma.
Yeah, so the question was, what rocket did they use to launch the Webb Space Telescope? And what was the second part?
Why?
And why?
They used the Ariane 5 rocket, which is part of a French space program, and it was launched from French Guiana. And there's a little story behind this. I don't know if Nuala managed to tell you. Before JWST launched, we had a baseline of 5 years of operations for this $10 billion telescope, and it would depend on how accurate the launch was. And the launch in the end was so accurate that the amount of propellant they needed to get it to L2, to get it to this million miles away, was so small that now we have a 20 or more year lifespan, right? The second part of the question was why an Ariane 5 rocket? That's mostly political. So ESA, the European Space Agency, has been a huge partner to the JWST. So often we see NASA Webb pushed everywhere. It's not just NASA that has built this telescope, it's also ESA. And ESA's space program is linked to the French space program, which is the Ariane 5 rocket in French Guiana. And I personally am so happy that they did, because they gave us a really accurate launch, a super long lifetime for this telescope.
Great, thank you very much. Any other questions? Yep.
Is there any way that we could use gravitational lensing to look at exoplanets?
Thank you. Did you hear that one, Nuala?
Yes, I did. So the question was, is there any way we can use gravitational lensing to look at exoplanets?
That's an awesome question which I've never thought about. Nuala, have you ever thought about that?
I have never thought about that, no.
So, the thing that you would have to have, is a very lucky alignment, that there's something in between you and that star or exoplanet that will be able to lens it. So it's unlikely, I think, that you would have a scenario where that lensing event is not going to be brighter than the exoplanet that you want to look at. However, if there was some wandering around black holes, maybe in the future, conceivably, like that sort of thing could be used. At the moment, I don't think it's part of what we can do.
Okay, I've got a question over there. Yep.
Given the huge sort of time frame to build these telescopes, do you have to start thinking about a successor already to the James Webb, or is this the end one?
So the question was, is there a successor to the James Webb, or is this the end one? Because obviously it took so long to build and launch this one.
So, even after Hubble was launched, and Hubble was wrong, people may know this, that it was looking at circular things and there were oblate. I think even before it was fixed, there were people in a room saying, what's next? And there have already been people in rooms saying, what's next from JWST? And the fact that we've managed to now launch a mirror that's larger than the size of the rocket into space opens up a whole new realm of possibilities. And so one that's been mooted is, rather than looking at the universe in the infrared, we look at it in the ultraviolet, which is another thing that you really want to get above the atmosphere. The reason we don't get too bad sunburn, etc., the atmosphere is blocking a lot of that light. There's one called LUVOIR, which would be 15 meters in diameter, used the similar kind of hexagonal shape and some of the similar design properties. So with all of these things, there's a long, lengthy design phase. There's like, will someone fund this, etc., etc. But there are definitely things in the pipeline already. What's next is a question we're asking very actively.
Thank you very much. Do you have another question? I can see at the back here. Hand up.
If it picks up infrared radiation, does it get very hot? As in, like, would it be hot enough to cook an egg or something like that?
Do you remember I was saying at the beginning that it's actually cooled down by special instruments to like almost absolute zero, so I think it's like minus 266 degrees. Is that right, Emma? Yeah?
Close to that, yeah.
Yeah.
Myriad, yeah.
Yeah. So, and because it's facing away from any heat and light from the Earth and the Sun, then it stays really, really cool. If it got hot enough to cook an egg, it wouldn't be able to take any images, so we don't want that to happen.
Thank you very much. Any question? You've got a question here? Yep.
Why does it need to be so cold? And also, we really like your earrings. Where did you get them?
They said, why does it need to be so cold, the telescope, and we really like your earrings?
Nuala, I think you've got why it has to be so cold. Yeah, so if we're deferred to me, if we want to look at the infrared wavelengths, that's like heat wavelengths. So if we don't cool down the instrument, rather than seeing the things that the astrophysical objects that we see, we actually see the heat from the instrument itself. So to be able to look at these objects, the instrument has to be colder than the objects that we're looking at.
Okay, there was a second part to the question as well. Nuala, do you?
What was the second part? Sorry.
The second part was, where did you get the earrings from?
Oh, I thought you said you liked them. Sorry, where did you get them? I want to know this as well, Emma.
Where did they get them?
Yeah.
Etsy, Cephid Studio. So if anyone knows what Cephids are, they're a type of star, so it's an odd spelling. So Google type of star Cephid, Cephid Studio.
Useful information. Great. Do we have any other questions? We've got time for one more? One more, yeah, great.
On the photo, like the pillars of the universe, I think it was called something like that, you could still see like the outline of the pillars on the photo in infrared. Like, why is that? Why can you see, like, why are there less stars behind the pillars even when you're looking in infrared?
So he is asking about when you look for the infrared and there's still dust there, you still see some of the dust that's there, so why do we still see some dust?
That's an awesome question. So often it depends what wavelength you're looking at. So sometimes when we see the dust that's there, we're looking at slightly longer wavelengths which see cool things. Normally dust, much colder. Some dust gets warmed up because it's close to stars or it's in the center of our galaxy, and so it can actually be warmed up enough that we can still see it in the infrared. It's all about its relative temperature to the things around it.
Okay, thank you very much. I think that's all we've got time for, unfortunately. So, very big thank you to Nuala for stepping in so much well at the last minute. Thank you for Emma for being available online to actually answer and field the questions as well. Really interesting. So a big round of applause. So our next CPC Cambridge Physics Centre lecture, it's on Tuesday the 15th of November in here, and it's on superconductors and their applications, and that's by Professor John Dorrell. So looking very much forward to seeing you there. Thank you for coming.